Hey and welcome. Today we are going to solve build array where you can find the max exactly k comparisons interview questions. There's a lot to explain, so let's get into it. First example here. We have n as 2, m as 3 and k as 1. This literally means our result array might be length of max 2. The largest possible number that we can choose to fill up those arrays might be 3, and we can have one possible chance to choose the largest number. The k here will represent our search cost, which means we only going to be able to choose k amount of max number as long as they are less than m's value, in this case 3. So we can choose one number as max value in this example. And by that, as you can see, first of all, each output array has n amount of lengths, which is 2, and only has k amount of max value, which is only one time. For example, in case of 1, 1, we have only max value once, which is number 1. In case of 2, 1 and 2, 2, again, we have chosen the max value k times, which is number 2. And one last time, in case of 3, 3, or two other 3 examples that we have here, we have chosen the max value once, which is number 3. Second example, with this combination of n, m, and k, there's no possible output we could generate because we cannot come up with an array that has a length of 5, which all elements to that array is 2 or any value less than 2. Plus, we could have 3 possible choices of choosing the max value. The main reason is since we have less m than k value, we can have an array with 1 and 2, but we always going to be left with remaining one choice of max value. So it's kind of not possible in this case. And last example, this time the value of m and k are equal, which means we only could have one value to choose as max and then repeat it n times, which leaves us with only one possible result of this. Also, we have one important note here in the question description. As the answer may grow, the answer must be computed modulo of 10 in power of 9 plus 7. Also, this is one of those questions that fall into the category of dynamic programming, since it really does not look for one actual answer that we could just simply compute or return, but it looks for different ways that we can get into the answer. This part I mean, return the number of ways to build the result array. Now let's take the first example and break it down. Since we only need to know the number of ways that we could construct the array, we don't really care about what those results array may contain. What we care is kind of 3 things. Number 1 is tracking the length of the array. Number 2, the max value that we included in the possible result array as we going through the algorithm. And the last thing is how many possible max values we can include in our possible result array. So why these 3 things are important? Well, we have the index tracker as something to check if we are not exceeding the value of n. Also, in case of this example, let's say we want to construct an array from ground up. We only need to know which number should be placed next in order to fill up the array up until the nth length, right? And for that, we have to choose a number max might not exceed m, considering being able to choose the max number up until the cap of k time. In order to choose such a number, we have 2 possibilities here. First, to choose a value that is not bigger than the max value. This will result us to save the quota of k we have and choose from the range of 1 until the max value we have chosen already. Basically a for loop. We will get into that part. Second, let's actually consume the quota of k we have and choose something that is larger than current max. This is so applicable when we start from 0. We don't have anything else to fill up the array, right? At that point. So we might go with choosing something bigger than the current max value to start, which is 0 at the time. Since both of those conditions will check for possibilities, we need a recursive way to accomplish that. Let's dive a bit deep into this recursive function. For result over base cases, we will only return 0 or 1 out of our recursive function and accumulate them as of our possible answer. But how we are going to define those base cases? And and also how we are going to say that we found a possible answer. As of our base cases, well, remember that IDX variable that we were talking about, keeping the track of how many items we have already added to the array through the algorithm. At any point, if that IDX value ends up being equal to the n value, that would mean we are done with that possible answer. And if in that case, we happen to have k as 0 as well, we might return 1 because we have one possible answer now. We have already consumed our k quota, k equals to 0, plus our array is filled up to its capped allowed elements now. On the other hand, we definitely want to decrement the k as we choose any max value, right? If that k goes below 0, we might return 0 from that recursive function, meaning that we are out of k quota or search cost. We can't continue with that case anymore. So that was our base cases. Now let's talk about how to choose numbers. Let's consider one of those 6 possible results out of our first example. At the beginning, both of those numbers are mystery for us, but we actually have 2 choices to make as we discussed previously. Either we can choose something that is less than the max value so far, or choose the max value and decrement the k once. That seems to be a good choice in this case, where we're starting to build our array because we just don't have any max value yet. So what we can choose here, let's check our arguments that we have, and here we go. Anything between 1 and n. Since we are dealing how many possible answers to this problem, this would be just one of our answers, right? That means a for loop over the range of 1 and whatever n value we have, and a call to a recursive function within that loop in order to calculate all scenarios for that specific index. So now we discovered that there are at least 3 possible answers so far. Now let's jump into selecting the next number. But here's the trick to the problem. Since we choose the first max value of our lives here, that also means we have used the search cost of k we had. For second number, we have to choose anything less than or equal to the max value we already have chosen, like 1, 2, or 3 in this case, up to the m's value, because that's the maximum value that we could choose. So if that is the case, for number 1 choice we had here, we can't choose anything more than 1, but we can choose 1 itself again, because we are allowed to choose the equal value to the max that we have already chosen. So that becomes another 1, and since we have n up to the length of our possible answer, now we are done with one result. For number 2, in this case, we have 2 possible options. Either we choose 1 or again 2 itself. And it's the same game for number 3. This time we will have 3 possible options to choose: 1, 2, or 3 itself again. And here we are with our 6 possible answers. Okay, that was the core of our algorithm, but 2 things before we jump into the code. Number 1 is it will perform well for a smaller range of arguments. But what about our constraints? N could be up to 50, M could be up to 100, and k could be less than or equal to n. If we have a case like n is 50 and m is 100, there's going to be a lot of recursive calls, right? So for that, as a basis for our top-down solution, we can use a memoization. We will create a 3-dimensional array for each layer of our recursive call stack to store the already calculated value and retrieve them for next ones in the constant time complexity. The second thing is the modulo part that question mentions. So as the calculations grow, we might keep our result in a boundary of 10 in power of 9 plus 7 like the question states. So we are going to wrap up the recursive calls with that modulo value. Okay, now this seems to be fair to code it up. Let's jump into the code and write the solution. First, we need to define our recursive dynamic programming function called dp, and matter of fact, we will return its result because that will calculate our answer. So since we want to create our possible array answers from ground up, we will pass 0 for the tracker index of I and also 0 as max so far value to kick off this function from the very beginning. Next, let's define our base cases. First one was if we reach to the last index in our possible answer. That means if our current I in recursion is equals to the given n. If that is the case, we want to return 0 here, but before that we need to check if our remaining search cost variable is finished, because if that is the case, we might return 1 from that recursion. Now after the second base case, whenever the remaining search cost variable goes below 0, we might return 0 accordingly, because we are out of k quota in that case. Now it's time to calculate the answer. Let's define the result variable. So remember that we discussed about 2 possible choices for each array element. Here's the first one. The case is, if we don't want to choose a max value, then we might start from 1 up to the current max value we have so far. And for each of those cases, do a recursive call to the dp function, passing I plus 1 as an index tracker to handle the work of keeping track of how many items we already have added to the possible answer array. And as I said, it might accumulate those answers from the recursive calls. Next option was, what if we want to choose the next biggest number that we haven't chosen so far, especially like at the beginning when we pass 0 as a value to the variable of max so far, or even what if we haven't reached to the max of m value yet. So for that, we need to loop over whatever value we have as a max so far plus 1 up to the m's value we have given. Then again, we will pass I plus 1 for handling the work about how many items we already passed to the result possible array, but this time we will also decrement the remaining search cost value because we are using our quota of k here. And finally, after those recursive steps, we are ready to return our result variable. Okay, this was the base case for our algorithm, but as I said, we need to take care of 2 things. First one was the memoization for bigger arguments we might receive. And second one was about staying within the boundary of our mod value. For memoization, we will create a 3-dimensional array for each of our dp states and fill it with -1 at the beginning. After creating our cache array, we will check if we had stored the value within our cache before reaching to the recursive calls, and if so, we will immediately return it. And of course, we need to store that value from previous recursive calls before returning them. So that was it for memoization. Now about the mod thing, we might define a constant of mod value at the very beginning and then consume it when we are accumulating the results of recursions. Okay, now we are ready to test our algorithm. If I run this, test cases are passing as you can see in here, and if I submit, we are in a good shape here and everything is fine. Let's jump into the time and space complexity. So the time complexity will be O of n by m in power of 2 by k, because we consider to have n by m by k possible states for each combination of arguments we get. For calculating each of those states, our second loop will run at O of n time complexity, and that is why we have m in power of 2 there. And actually, the memoization helps us a lot to reduce the cost of time and avoid calculating twice, as we discussed and saw in the code. The space complexity will be O of n by m by k because of recursion call stack, but overall we have n by m by k possible state for our DP solution that our memoization takes up the space for it. So that was it for this video. Thanks for watching, and please leave a like, comment and subscribe to the channel. I will put the link for dynamic programming playlist in the description and a few other playlists as well for you to check it out. And finally, hope you enjoyed this video and stay tuned for the next one.